Good. So, welcome everyone. Today we will have a seminar, and our guest is Dr. Emil Allegrot, uh, an expert in automated GUI-based testing. Have been doing research for more than 10 years in the minimum, and we are at Syntheta very happy to have Dr. Emil here and talk about this testing. I will just give a brief about what it is, and you will have more a description of what Emil will talk about. So it's in small words. It will be about automated software testing, which is the modern software development containing continuous integration. And I hope this will help you further. And this is one of the several seminars that we are planning to have Dr. Emil with us discussing the testing. So I'm happy to welcome Dr. Emil, who will take over now. And here we go.
Welcome to this lecture. My name is Emil Allegrot, and I thank Michael for the introduction, and hello to people in the room as well. So in this lecture, I'm going to give a little bit of an overview of the testing area, both in industrial practices as well as some academic practices that we're doing research on. I'm also going to touch a little bit on continuous integration, since automated testing is very related to the topic. But first of all, before we start with any particular techniques and stuff, I want to talk about the difference between verification and validation. These are two different terms that are often confused in industry, or that there are misconceptions about. So when it comes to verification, this is the practice of ensuring that the software that we've developed conforms to its requirements, to the requirement specification. And if we take a good old model like the old V model, where we have requirements on the left side and testing on the right side, we are going on the top left side from users' needs and what the customers want in the final product. And we generally then have some business analysts or requirements engineers that elicit these requirements from the user. And then these interviews or whatever it might be are transcribed and turned into high-level requirements that are generally then on a feature level of abstraction. These requirements are then filtered down further into functional requirements, into further on into user stories, for instance, and then sometimes all the way down to specific algorithms before they're turned into code. And if you think about all of these different steps, then on the right side of the V model, we then have different types of testing activities that we can do for each level of these different requirements. So for algorithms, etc., a user story level, we can do things like unit testing, we can do static code analysis. When it comes to functional requirements that generally consist of multiple components put together, we need to think about interface tests as well as integration tests. And when we come up to a feature level of abstraction, we need to think about things like GUI testing, or more explicitly system level testing, where we incorporate everything. But when we think about all of these things, as I said, the feature requirements are refinements of the user's needs. So what we're talking about here is still verification of the requirements. And why verification is then focused on the requirements is because when a user describes their needs, the person eliciting this might misinterpret, or when you try to concretize these requirements from the user's needs, you have to make assumptions, because you're going from more abstract information, being the needs, into more concrete requirements or more concrete information. And the same goes when you go from feature requirements to functional requirements and further on and so forth. For each of these steps, you need to make assumptions about how to concretize it. So many people or researchers akin this concretization of requirements to the whisper game. If you've ever played that, it's sort of that one person starts and says a sentence, and then you whisper that to the next person and the next person, and then in the end you get this really funny sentence that has nothing to do with the original sentence. And the problem is when you do this type of requirement breakdown is that you get the same issue. So when you're doing the tests, you're testing sort of the whisper game that might not be the actual requirements or the needs or fulfill the needs that the original customer had. And so this works well then for verification. But in order to get around this problem with the whisper game, we also need to do validation. And the validation is to ensure that the system conforms to the actual customer's needs. And what this means then is that we have to have real customers on site in order that use our software, and because they are the only people that can say that the software is actually valid to fulfill the needs. In industry at large, this is very costly and so on. So therefore, a lot of validation is also done with what is referred to as customer proxies. And a customer proxy is then a person within your own organization which has a great deal of domain knowledge. So they understand the actual customer's needs and can therefore act as a proxy to do the validation. But in short then, if you take nothing else away from this lecture, try to remember these two core concepts, the difference between verification and validation, because this is more important than you might think. So if we then start to talk about some different types of testing, what we need to consider when we do testing, regardless if it's manual testing or automated testing, is that the testing has a purpose. And different techniques have different strengths and weaknesses, like everything else, benefits and drawbacks. So we need to first consider what are we trying to do, what type of test are we trying to, or what type of testing are we trying to achieve. So the first one on the lowest level of abstraction is that we do some type of component test. And the component in this case can be anything from an algorithm to a function to a small unit of code. And here we talk about unit tests. And unit tests then are basically that we send some input to the component for which there is an expected output, and we check that the actual output from the component conforms to the expected output. If the actual and expected are the same, then the test passes and it goes green. But if it's anything else from the expected output, we say that the test failed, and we need to do some updates to the component, well, most of the time. Then, but components are generally put into a context within some architecture where components work together. So inputs to one component produce new outputs that are the inputs for the next component, etc., etc. And we can then see that as a group of components like this. And this is where we want to start doing integration testing. We want to integrate that the components work together. And one way of doing this is simply to send an input to the first component. I hope you see, can you see my mouse online? Yeah. So if we assume that this component over here is the first one, we send an input to it, it produces an output that becomes the input for the next component, that produces an output, becomes the input for the third component, etc. And what we do then is that we send an input to the first component, and then we evaluate the expected output of the third component. And what we then check is that the communication between the components is correct, because if the output from the first component doesn't match what is expected as inputs for the second, etc., then we will get the wrong expected value in the end. However, this isn't necessarily a check of the functionality of the components, but rather that they can communicate with one another, that they integrate with one another in a suitable way. So input-output interfaces match. Integration testing is, though, a little bit special in this regard, because we can talk about integration testing here on a very low level abstraction, basically being functions that send inputs to one another. But we can also talk about it on a subsystem level. And on a subsystem level, each of these two subsystems could be in the order of millions of lines of code. So could be very huge systems, but they still need to be integrated with one another. And when we talk about it and on this level of abstraction, we still consider inputs for one subsystem that produces outputs to the second system, and we check that these interfaces between the subsystems are working as intended. So it's still classified then as integration testing. Then on the even higher level, we need to start thinking about end-to-end scenarios. And this is where we get into system testing. And since most systems today are graphical user interface driven or have a graphical user interface, even though command line interfaces and so on still exist, even though they're uncommon, here we need to incorporate also then the graphical user interface into the testing activities. And for some system, like I don't know, I was about to say nuclear power plant, but let's say that it had just a start and a stop button. We can assume that the power plant has millions and millions of lines of code, but there might be very few graphical components to control it. This might be a silly example because I assume that there are a lot of dials and stuff in a power plant, but you get the point. And the thing here is then that for these tests, very few interactions on the graphical user interface level can then stimulate a lot of code underneath it. So even with a very few set of actions, we get a huge coverage of the code. And this has some benefits and drawbacks that I will get back to. But in short, think about the purpose of your test. Do I just need to test this little function? Well, then you should go for a unit test rather than maybe an integration test or a system test. However, if you're interested in the whole chain of events throughout the system, then you should focus more on a system level type of testing. So in conclusion, then different tests require different methods and tools, and there is no test to rule them all, so to speak. They have different strengths and weaknesses, and as a good tester, you need to balance and know these different benefits and drawbacks to use the best appropriate approach. So if we go into some different types of test techniques, then very nitty-gritty. The most common industrial practice that is still used today is still ad hoc testing. And ad hoc in this instance doesn't mean random, just do random stuff. It means for the purpose of. And this could be then, for instance, if you're doing programming, you add checks within the code. It could just be print lines, or it could be what's it called, check marks in the code, just to check that the state of the algorithm is in the right place in a certain certain time point. I got hung up on the word. It's checkpoints. You add checkpoints to the code. In any case, the issue with ad hoc testing is that it's not necessarily structured, which implies then that it might not be replicable. However, this could be fine because the purpose of these tests is generally to check that the functionality you're working with at the moment works as intended. And so this is then very common just to do intermediate checks. Another common technique is exploratory testing. And here there are also some misconceptions about how to do exploratory testing. And it's often assumed to be random testing, that you simply maybe click around in a GUI, you find a faulty behavior, you report this faulty behavior, and then you randomly click around for finding the next faulty behavior. However, this is not how to do exploratory testing. What I just explained is more akin to random testing. So what's different than with exploratory testing? Well, as you see there, the definition of it is simultaneous learning and test design. And what this implies then is that you start with sort of a random approach, usually on a GUI level abstraction. When you find a fault or a strange behavior, you try to narrow in on exactly what actions that trigger that faulty behavior, and then you report that minimized set of actions as well as how the failure manifests. And then this is all then sent to the developers as input to replicate the failure and to identify what the actual defect is. Because when we're doing this on a GUI level of abstraction, we don't identify the actual bugs, we identify the failures that manifest from the bugs. And so we need to identify from the failure the root cause, and this is called root cause analysis, identify where in the code the bug is that is causing this manifestation. And some exploratory testers, of course, go all the way, so they find a failure and they do the root cause analysis, but most of the time is reporting the steps that lead up to the failure, and then it's up to developers to identify the actual bug. The next one here on the list is smoke testing, and smoke testing is the name came from the good old days when we were doing more computer science, putting circuit boards together, wiring them up, and then hitting the power button and looking for smoking circuits, basically. And the smoking circuits then being short circuits, obviously. But the name is sort of stuck around, and it's also used then in software testing. And when it comes to software testing, obviously we don't have smoke coming out of the software, but rather this is metaphor then for obvious faults. So it could be that you finish your the function that you're working with, you integrate it into the system, you set up on your local computer or in a reference system, and then you do some quick checks to see that you don't get obvious things like blue screen of death or that the application crashes or something like that, which is then akin to the smoke that you're looking for. And this could then be more semi-structured because you can document a little bit how you do it or record the steps that you did, so you can then use it in later to, with the same scenario, to see that you have fixed the problem that appeared where the smoke was. Then the next one here is regression testing, and this is also super common in industry, but regression testing is a little bit different from the others here, that you can do regression testing on any level of system abstraction. So you can do unit regression testing, you can do integration regression testing, and system regression testing. And the purpose of regression testing is simply that if we have a working version of the software, we create test cases for it, we make sure that all the test cases pass, that they go green. Then we obviously do updates to the software, maybe for the next version of the software, and then we run the same test suite again. And if any of the test cases that are part of the system that we have not touched fail, then we see that we have regression issues. So here's a misconception also when it comes to regression testing in industry, and that is that regression tests do the right thing when they fail. But in reality, regression tests do their thing when they do not fail. The default condition for a regression test is that it's supposed to go green, because the way you should work with this is simply that you create your regression tests for the first version, everything goes green, everything is done, you release. Then you do updates, and when you do updates to the code, you should also update your tests. You should maintain your tests. So when you run the regression tests, they should all go green right away because you have updated both the functionality and the tests. However, this type of proactive maintenance is somewhat uncommon in the industry because it turns out when you have a test suite of 10,000 test cases, which you can have for unit tests, it might be tricky to figure out which changes to all parts of the code that are connected to what test cases. So it's much easier then to run all the tests and see which fail, and then backtrack to see, did we do changes to the code? Yes, aha, it's not a fault in the test. We'll simply update the test, and then it goes green again. However, this is then somewhat costly because these failed test cases then that have not been updated, they are referred to as false positives. And since you don't know if this false positive result is caused by a fault in the test or an actual bug in the code, you still need to do root cause analysis to figure out if it's the test or the code that is wrong. And this then adds additional overhead costs to your development. So yeah, proactive or reactive maintenance, it's what works best for a certain organization. Then the last part, which has become more important in recent years, is quality testing or testing of non-functional attributes. And non-functional attributes are these additional aspects of software that are important for the customers, such as performance, security, user experience, usability, learnability, etc. There are also these internal non-functionalities like maintainability, understandability, and so on, scalability, etc., etc. And from recent studies we've done, we have found that there are like 5 or so ilities, as they're also referred to, that are more commonly tested in practice, which include then, in particular, performance and security. But this is an area of testing that is becoming more and more important because it can also be used as a market benefit to get market shares. For instance, consider that you have our software or the software at the company, as well as a competitor software, and both of the softwares do the same, have the same functionality, but one of the softwares has higher performance. Then it might be that the customer will go for the software with a higher performance just because, well, it's better, especially if they're in the same cost range. Then when it comes to academia, we're doing some interesting things there that haven't quite made their way into industry yet, but that are sort of on the verge of getting there. Test generation is one of these things. This is something that academia has worked with for, I don't know, 40 years. And we have some really powerful solutions to create a lot of test cases. So basically the idea here is that you start with something, and then you mutate it, or you use meta heuristics, or you infer, or you do something to generate a lot of similar but still different test cases. So creating millions of test cases. The benefit of this is, of course, then that you get huge test suites that give you high test coverage of your code and functionality and so on. But the problem is that when you do this, many of these techniques are quite stupid, meaning that they generate a lot of test cases that don't make sense or don't add any real value. So for instance, in a GUI level abstraction, you could get a test case that clicks on the start button 17 times. And what's the value of having that? Will anyone in reality really do that test case? Well, maybe not. So the issue with many of these then generated test cases is that they find these fringe defects that are very, very unlikely to happen in reality, because they trigger scenarios or paths through the code that are so that will never really happen in actuality. Then we have automated testing, and with automated testing here, I don't mean automated testing as what I'm talking about generally in this talk, but completely automated testing, meaning that there is no human interference at all. You simply click on a button and you get bugs in the end, and the tool does everything in between. And here we have techniques like fuzzing, meta heuristics again, ML and AI are starting to pop up here, of course, but still, this is a very new area where it's something that academia has been hunting for many years, but we're still in the early stages of it, where we're starting to see some techniques that can sort of infer the functionality of the system through, for instance, observing the human behavior and then generating test cases. The problem here when it comes to completely automated testing is when you, what is the oracle? How do you know that one of these generated automated tests are doing the right or have found a faulty behavior? So this is sort of where humans come in, because humans are very good at identifying that, well, this isn't what was intended when I did this or clicked on this function or used this function, but a computer could have trouble identifying that, even though there are some techniques that are moving towards acquiring these automated oracles. Then we have model-based testing, and model-based testing is one of these techniques that is a little bit misunderstood again, because when we talk about model-based testing, we have to start with what do we mean by a model. And most of the time when you say models, people think about boxes connected with arrows to other boxes and stuff like that, so design models. But in essence, everything that is an abstraction of reality is a model. So for instance, a Barbie doll is a model of a human, and a model car is a model of an actual car, etc., etc. This means then that even the requirements that you create for a system is a model of the actual software in the end. It's just more an abstraction of the functionality that is supposed to be in the actual software in the end. So when we talk about model-based testing, MBT, then we often talk about models that are visual models, where we have these boxes and stuff connected to code. But we can also talk about other types of models, like in behavioral-driven development, BDD, or test-driven development, TDD, where we use actual test cases or test case descriptions as our model of the intended behavior of the software. And this can then be used then to stimulate or identify new defects and do almost a little bit of exploratory testing, but I use that term very lightly here. The next one on the list here is mutation testing, and this is very different from the others because mutation testing or mutation analysis is not intended to find defects in the software, but rather as a test of the quality of the tests. So what you do in mutation testing is that you calculate something called a mutation score, where you take the software that is working and you introduce artificial defects in it. And with the assumption then that our test suite, our collection of test cases, is of high quality, it should find all of these artificial defects, all the mutants. And the mutation score then is calculated as the number of killed mutants, being identified mutants, divided by the total number of introduced mutants. So it's simply the percentage of killed mutants. And these words I'm using is here, killed mutants and so on. They might sound funny, but that's the actual academic nomenclature for it. That's what the consensus in the academic community, how you refer to these things. Then the last one here is formal methods. And formal methods is one of these things that has been around as long as software has been around. And the idea here is that you do mathematical proofs before you start developing the software to basically do, well, mathematically prove that there are no defects in the software when you develop it. The issue with this is that it's, of course, extremely costly, and it also requires that you use certain programming languages when you start implementing the proofs. So you cannot use, for instance, Java due to, for instance, the garbage collection in Java that is adding all of these side effects that you cannot control for in your mathematical formula. So therefore, this is super expensive. It requires a lot of specialized knowledge, and therefore it's only used in a small array of companies, including, for instance, NASA. They use this. So software being sent to Mars, etc., they are proven to be correct before they're sent up, for instance. So not a technique that is that common in practice, I would say. I've already mentioned regression testing a little bit, but here's just a visualization of it. So assume that we have a system version 1. We create a test suite, a set of test cases for version 1. Then we do check that all the tests pass for version 1 in the test suite. Then we create our system version 2. And what we do then is that we take our test suite from version 1, we repair the tests that are no longer valid for version 2 because we've changed the functionality. And then we add additional tests to the test suite for the functionality that we've added to the system. Then for version 3, we do the same thing. We update the test cases that have been changed, and we add additional tests for new functionality. And this means then that we just continuously maintain our test suite over time. So the goal of regression testing is to verify that changes to the system have not broken parts that previously worked. That's the intent of regression testing. But the implication of this, in order for it to work, is that we have to maintain the tests all the time. And this can be extremely costly, especially when you have huge test suites on multiple levels of abstraction, being both unit tests, integration tests, and system tests, and so on. So then we need to talk a little bit more about high versus low level testing then. So a view that we can consider when we look at the software, most of the time when we consider a software, it's sort of a black box where there is functionality within the black box, and we send some inputs and we observe some outputs. However, if we want to talk about root cause analysis and more detailed types of testing, we can consider it more like this, like a spider web of functionality, where these nodes here on the very top level here could be just buttons, for instance, on the GUI. And then we have architectural components beneath here, control code, etc. And then at the very bottom here, we might have our functions or algorithms that do some calculations for us. And if we trigger some type of function here on the GUI, that will, of course, find a path through the system down to the right algorithms that execute something, and then the results are sent back to the top. And the issue is then when we're doing high-level tests on the GUI level abstraction is that we don't know when we observe a faulty behavior where the bug is. It could be in the small component at the very bottom, the algorithm that is incorrect. It could be a logical or arithmetic issue, for instance, but it could also be in the control code in some way that we've been sent to the wrong algorithm that is doing the wrong thing. And it's impossible for us to know this from the GUI level abstraction. And this is then where root cause analysis comes in to identify where in this huge structure of the code that the issue is. And this is where it's important then to have some traceability and stuff like that within the architecture. So it's easy to identify in what parts of the system that the potential issues are. So basically, when we approach this from a black box perspective, right, the GUI level abstraction, we can see the GUI as the top of the iceberg. But the major work we need to do is with under the surface, so to speak, where we might have millions and millions upon lines of code. So high level, we only see the failures, manifestations of defects. So we must do root cause analysis. However, if we then do low-level testing, being, for instance, unit tests, we can, when they trigger, since they're so close to the components or so close to the code, they generally flag almost exactly where the defects are. But the problem then with low-level tests is that they can't say anything about, if I found a bug in this function, how will that manifest on a GUI level of abstraction or higher up in the architecture? So we sort of need both. So if you do a little bit of comparison between then manual testing and automated testing, and then also between high and low level testing. For manual testing, and in this case, I'm talking primarily about manual regression testing, where you have these tables of steps that the human reads, like click on button X, observe behavior Y, did that happen, yes or no, check, followed by the next step, click on the next button, observe, check, 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 check. These test cases, they are generally created directly from the requirements and mirror the requirements really well. And because of this mirroring, it is the development cost of these tables is sort of on average, because you need to do a lot of analysis of the requirements in order to formulate it as test cases. The execution cost of these manual test cases is, however, very high, because you take your highly skilled developers most of the time, they cost the company a lot of money, and you put them in front of a computer and they sit there and read and click on the screen for many, many, many hours. In most companies that I've seen that use this, normally larger scale companies, these test suites take in the order of weeks to execute by multiple testers. So it's enormous cost every time, and it's only done then quite seldom before larger releases. So high execution cost. However, the maintenance costs of these tests are quite low, and this has to do with the cognitive ability of humans. So for instance, assume that it says, click on the exit button, okay? And then the human would look at the screen, they wouldn't see a button that is red that says exit, but they might see a little button with an X on it in the top right corner. Then we would make the cognitive conclusion that that must be the exit button. And we click there, and if the observed behavior is the software terminates, then we can make the assumption that we did the right thing. So we can leverage the cognitive ability of humans there a bit. However, then for automated tests, the development costs are considered still average to quite high, because we need a lot of tests on many different levels of abstraction. So for unit testing, the cost here is quite low, depending on what types of tests you do. But the further up you come in this chain of different tests, so it becomes more and more costly. And when it comes then to execution costs, though, since they're automated, there is no cost. They run automatically on a continuous integration server somewhere, and this no cost is a little bit true with modification, because the human still needs to analyze the test result, but the execution itself is then just the energy power that you pay for the server running, which is also quite high nowadays, but still very low in comparison to the manual execution cost. Then, however, when it comes to maintenance, then the costs really become an issue. So for automated tests, since they are generally scripted or very well defined to the specific context of what they're testing, they don't have this leeway like the human does to assume that a certain behavior is correct. They look at the exact outputs or exact data that's coming out of the system, and if it doesn't match, they flag it as a failure. And a human then needs to analyze this and figure out if it was a false positive or a true positive, and depending on that, update either the code or update the test. So maintenance issues. And then when it comes to low versus high level testing, then referring to the previous slide, when it comes to low level tests, then the number of tests that you need and a unit testing level of abstraction are quite many. You would need at least one test case per component, basically. However, if you take things into account like boundary value analysis, which is a common way of thinking about which test cases to create, then you need a lot more than one test per component. But worst case, you at least have one test per component. But if you then have a large system, of course, with many millions lines of code, then you quickly get a lot of tests as well. Makes sense. The benefit, though, is that when one of these unit tests trigger, you find a defect almost directly because you know exactly which component that is, where the defect is. On a high level of abstraction instead, then, as I said, even if you have millions of lines of code, you might just have a few buttons. So that means that you don't need that many test cases. But the problem here, as I've explained already, is that you find the manifestation of the defect, the failure, instead of the actual defect. So you have to do this root cause analysis. So benefits and drawbacks once more. Then we have unit testing and a little bit more technical stuff about this. So you get to see an example of what they might look like. And unit testing is generally done with X unit frameworks. And X here stands, you have to replace that depending on what programming language you're using. So for Java, it's called JUnit. For C++, it's CPP unit. For C#, it's NUnit, etc., etc. And the reason you have all these different frameworks is because the frameworks need to interact with the actual code that you've developed. And run code as part of the tests. So JUnit then for Java, for instance, is basically written in Java. It's a Java framework, but it has some additional methods that allow you then to trigger and do assertions of code. So what does this code then look like? Here's an example from C#, where we are testing this small calculator class, so to speak, with a method called multiply, with that takes two integers as input and returns the product of the two integers. And if you look then at the first test, we see there that what we start doing over here is that we generate a new instance of our calculator. We then calculate the result, which in this case is -1 times 3. And then we do what is referred to as an assertion. We assert that the output is correct according to some expected output. And the actual output in this case is then stored in this result variable, and we compare it to our expected output, which is -3. And this is then what we refer to as a happy path test, what the system is supposed to do. Or a positive test is also a word for it. And the second test here is in the same line. It's also a happy path test, but the last one down here is more of what we refer to as a negative test case, where we check what the system is not supposed to do in essence. So what we're doing here is that we're checking that if we're inputting 1 and 2, we do not get a calculator operation invalid exception, which we might get if we, for instance, send in a string and an integer, or two strings, because we can't add or multiply them with one another. And these negative test cases then can be very powerful because we then check every condition that should not happen. So for instance, assume that you have a percentage calculation, which is only supposed to be in positive percentages between 0 and 100. A nice negative test case to this would be then to send in -1. or minus 55 or something like that, a negative percentage. And you can then assume that if you get a strange behavior for -1, you would get the same strange behavior for -55, because that's just how it is. So negative test cases are good. However, when it comes then to these types of tests, since XUnit frameworks are generally designed in a programming language that they also aim to test, you have access to the entire programming language when you're creating the actual test cases. So you can use things like for loops, if statements, and so on as part of your tests. And I have seen examples in industry where the test cases are more advanced in terms of well, complexity than the code that they're testing. And this is when you have designed things like with multiple loops and so on to try to replicate behavior of the functionality that you're testing, for instance. So this is a very silly example that I show you here, but it's just a way of sort of showing that, well, remember that you can do more advanced programming as part of your tests if you want to. Then the XUnit frameworks can also be used to drive other types of tests. So you can, for instance, use it to drive GUI level tests or system tests. And a common way of doing this is with the Selenium framework, where you include the Selenium framework as part of your test environment. And then you use something called XPaths in order to identify the individual components in the web browser. And then XPath can be akin to basically a URL to the component. So it's a link to the component. And if as shown in this case, this find element component finds the widget it's looking for, it will return something to the element variable, lm variable, and otherwise null. So if we wanted to check that a certain button exists, for instance, on the screen, we can do something simple like this, that we assert that lm isn't null. If it is null, then we never found it. And if it's not null, we found something. And it's sort of a high-level test that the system seems to work. An issue, though, with this type of technology using, for instance, Selenium, is that the Selenium is defined as a GUI testing framework, but it operates against the GUI model, or what is also referred to as the DOM model, document object model. And the document object model includes all of these URLs and just paints basically how a web page should be rendered in the web browser. It's not the actual GUI as shown to the user. So here's a small example where I created a very small little application, which just has this input field and a submit button and a cancel button. And then I ran Selenium against this and got the following output, where I extracted the background color of the submit button. And I got the RGB code, which says that there is 0 red color in that button. There is 128 green color and 0 blue color. So that button is not blue, according to Selenium. So what happened there? Well, what happened here is that there is a bitmap image on top of the button, but the background color is set to green. And this can cause issues when doing relying too much on these tests, because you could have, for instance, here a broken button or set up your test case in the wrong way, and the test case would say that everything looks fine, and you ship it, and then when a human looks at it, it's like everything looks completely crazy. Another example here is if you have moved the button, you could have a button outside the visual area. So for instance, move it to the left in the web browser, so it's outside the screen. But since it's still in the document object model, Selenium would still find it. So it would still do the actions on it and everything and say that everything seems to work fine, even though it's not even shown on the GUI. So a human would never be able to use it or even find it. So that's an issue. So an alternative then to using Selenium is to use image recognition-based tests. And one framework we have available here at Syntheta is the I2 library, which allows you then to use image recognition inside your XUnit tests. And basically, they work similar to the Selenium test, but instead of using this XPath, it uses image recognition to identify the visual component as it's shown on the screen. So if you were to run the same example that I did previously with Selenium, but with image recognition, we would see here that the visual test fails because it was looking for the blue button, but never found it because the link is broken. So it helps us a little bit in this actual UI testing. But in reality, test cases are never the simple that I've shown you. Rather, it looks something like this. The stuff I have up on the screen here right now. This advanced testing with radar object X is a new radar object with a radar plot that is blue, and then you assert equals that 2x GGH53 is something large string and GGH. And to us here, or you online, this makes no sense whatsoever. It doesn't even make sense to me because this is random gibberish. However, it's inspired by actual tests that I've seen in reality. And the reason why I bring it up here is because we here, without the domain knowledge, cannot interpret if this is a good or a bad test. But a domain expert that, for instance, Saab, that developed radar systems, might look at this and say, GGH53. No. It should be GGH52 down here in the assertion, right? Because that makes sense to them based on their domain knowledge. So the idea here is that in order to become a good tester, it's not enough just to have the technical knowledge of how to write test cases. You also need to know what to test. You need domain knowledge to understand how the system is supposed to work, preferably how it's being used by the user in the end or in the user's domain. Then, talking about some more stuff that we have here at Sintida, we have access to two tools called iAutomate and HiveMind. Starting with iAutomate, which is the tool here to the left, it's a GUI-based testing tool using image recognition. And it has this neat little interface where you have a text area here where you can write scripts if you want to, or you can use the macros here to the right. And what happens when you click on one of these macros is that the tool will prompt you to take a screenshot of the image that you want to interact with. It could be to click on or just find somewhere or drag and drop or whatever it might be. And then you create test scripts of steps that emulate the human user. So this is then very good then for system level testing, end-to-end scenarios. And the key benefit of using image recognition in this case is that you don't have to care about the technology of the system under test that you're testing. So it could be a mismatch of different programming languages. For instance, you could have a front end that is HTML, but the back end is, well, C++ or whatever. And you could have then the tool interact both with the front end, but also go into, let's say, a CLI or just manipulate files, whatever, as long and send that directly to the back end to see that something happens on the front end. And this, the power of this is then that you can do basically automate basically anything a human would be able to do on the screen, since you're using the same interfaces, the GUI, what is shown on the computer monitor, as well as the keyboard and mouse, same way as the human. So very powerful tool, worth looking into. The second tool is HiveMind, and HiveMind is today, currently, a web-based testing tool that is using Selenium in the backend to identify components on the screen. But the main benefit of this tool, or the main thing with this tool, is that it's using this augmented graphical user interface where additional test information is rendered directly on the system under test for recorded test cases, for additional information, these graphs, the test model, etc., etc. And the idea here is to provide then suggestions and aids, visual aids to the testers to create more powerful and better test cases. In particular, this model that you see here, this blue thing here, this is being recorded every time a user uses the tool and click on something new. So new test cases are being created. In the back end of the tool, there is these smart algorithms that continuously analyze these test scenarios and test data in order to generate new test cases and new test data. And these are then provided back as suggestions to the user and it becomes then a type of human-machine symbiosis where you continuously create better test cases. So if you have web-based systems that you want to test, this is definitely something that you should look into and try out. Then I want to finish off with a little bit about continuous integration, because the automated testing and all the testing I've been talking about currently is part of modern development techniques such as agile software testing and then also continuous integration. So what is the core purpose then of continuous integration? Well, it is to get rapid feedback about our system that we're developing. And this is achieved then through automated builds and automated testing, where we want log files that the builds work or go through as intended, that everything builds and integrates correctly. And then we want to run tests on top of this on different levels of abstraction to make sure that both components, integration, and system level stuff work as intended. However, in order to do this, this requires that we at least have a build server and some automated tests. And this figure up to the right here visualizes a little bit how this is intended or intended to work, where we have the user that uses an integrated development environment of some kind to create code and tests. These are being sent to some repository, it could be Git, it could be Subversion, it could be something else, and where you do merges of the code to create some type of, well, release candidate. And this release candidate is then, well, it's not the release candidate, you just have the code there. But this is then pulled to the build server that that builds everything, basically compiles it, and then runs automated tests. And the results of these are then sent back to the user in order to see if everything worked as intended. And since these systems or these tool chains are automated, you can do this many, many, many times per day, and then get very quick feedback that everything you have changed, updated, works as intended. Remember what I talked about, regression testing in particular. This is very important in this type of environment. Another thing within continuous integration is that it allows you to be more agile in terms of change. And here I'm not talking necessarily about agile software development, the process such as Scrum or extreme programming, something like that, but just being agile to changes in the market or changes in users' needs. And once more here, regression testing is very important. However, in order for this to work really well, you need to have a well-maintained architecture in the software, as well as traceability among different artifacts. And this is then exemplified here with these three boxes, where we have here the first one, a high-level requirement, for instance, a feature which has a gist, that a brief description of the requirement, and then some type of long description of the requirement. This is then broken down, remember the whisper game, to maybe a user story of some sort, which also has an ID number, but then it should also have a reference number. Where did this come from? Well, it's a breakdown of requirement 1, and therefore we have this reference here in the user story that it connects to this requirement. And then we have this description in the user story. As a user, I want something because reason. And then we have our test case, and this once more then should include a reference at least back to the user story for which the test case is created. And this could then be not necessarily just a textual artifact, but actually a working unit test, for instance, with a comment in it that says that this unit test is connected to requirement X or user story X. It's a test for that. So you have this trace, and these traces should then continuously be maintained. So when you're doing changes to the source code, you also update this documentation so you can trace things back and forth. And why is it valuable? Well, it's valuable when you get a trouble report from, let's say, your customers that say that a certain function isn't working as intended or something like that, a feature isn't working. Then you can go into your requirements and see, okay, which feature is this is the wrong one here? Okay, and then forward track to the test cases and see why is this test case not finding this failure, and then you can update it, for instance. And a tool to do this a little bit smarter could be Jira, for instance, that has functionality to add this traceability really easily. Then the last thing that continuous integration helps you with is team-based development, and in particular the things then like merging of code from multiple users. And to do this, you require some type of branching strategy. You should never, ever, ever work against this top arrow here, which is then called the trunk, or the main branch of the application, because that should always be working code. That should always be able to compile, send through the continuous integration environment, and be sent out to the customer at every single point in time. And this is where branching comes in. So every time you as a developer get a new ticket to work with, you should then branch out from the trunk, and you can branch multiple times if you want to. This could be multiple branches in multiple teams, but you should work within this new branch from the trunk so that you don't mess up the working trunk, for instance. So, and these branching strategies, there are multiple well-defined ones. Microsoft has one, for instance, that you can read up on. Just Google for it, or you create them ad hoc in your organization. But this is still something that's very important, so always make sure that you have working software. And with that, I'm actually done. Thanks for the heads up, Michael. I just got a note that I have 2 minutes left, but I'm ending it here. And yeah, a lot of information, but I hope that you learned something. And if you have any questions, feel free to shoot now. Otherwise, well, you know, most of you know where to find me.
Well, thank you very much, Emil. I would like to share experience that we had with Re-Ink. We released the product last week, and we saw that this kind of branching is very important. You should not work directly on that. And that's what the team did, and we had a big problem. So I remember from my old days, every new thing that you introduce into the code, you have high risks for doing bugs, introducing bugs. So how do you see, just connecting this to your like testing approach, what is the optimal way of one going live? What should you do? I mean, should it be like test suit that you see, okay, during this week we will freeze the branch, and we will only do this kind of test, and we will only work with bugs that are like high priority, showstoppers, or whatever it is. What's your like idea on that?
This is a very tricky question. It's a good question, but it's a very tricky question because it can be very context dependent. So you have to consider basically what is the best case scenario where everything is working as intended, where you're planning for releases and everything work out as intended, versus where everything goes to hell, so to speak, or where you overrun the time for development and so on, and you don't have the time for testing, proper testing. So if you have the best case, then you have a nice setup of automated tests that continuously run with every build and everything to continuously monitor the quality of the software. However, in the worst case, then especially if you have manual testing at the end, then you obviously have to prioritize. What are the most important features or the most important things that we need to deliver to maximize our customer value in the end? And this would then be that once more then keeping track of which are our core requirements and how do the traceability to our core tests, make sure that the core tests, that they at least pass. That is super important. For new functionality that might be more experimental or stuff like that, if you have a good branching strategy, you can choose not to include those branches in the release, for instance, if the tests show that they're not adequate quality and stuff like that. So you have multiple tools to work with there. And so in the end, it becomes sort of this business decision versus quality decision. But I think that one important thing here is to give mandate and entrust your developers in that they do a good job, that they develop software with high quality as well as test with good quality. And if they say close to release that we're not ready, you don't release it. But that's not always possible, of course, because you have customers that will be like, yeah, but release it now or we go to your competitor. And then, okay, then you do what you can with the time you have.
Exactly.
So
yeah, I see that the time is out. Thank you very much, Dr. Emil. I will say again, we really are happy to have you here talking about this, and we will for sure have a follow-up on this seminar. And everyone understand here, we need to do more tests for sure on everything before releasing it. So thank you again. And if there is any questions or thoughts, you can just send it to emil@syntheda.com or to the administration, Carla, at syntheda.com. Okay, thank you very much, everyone.